Imagine standing before something so vast that your brain refuses to process it. Not because it's beautiful, but because it feels wrong. Across the planet and the universe, enormous structures exist that defy logic, physics, and expectation. They were never supposed to be possible. And yet, here they are. Across the globe, humans and nature alike have produced structures that defy comprehension. Some are vast monuments of engineering, scale challenges expectations, pushing the limits of physics, engineering, and endurance. They exist today as evidence of ambition and power, yet their very size invites a simple question. They should not exist. Consider the Great Pyramid of Giza. Constructed around 4,500 years ago, it remained the tallest structure in the world for over 3,800 years. Standing at 146 meters originally and weighing an estimated 6 million tons, it is composed of roughly 2.3 million blocks of limestone and granite. Each block weighs between 2.5 to 15 tons.
The location of the Great Pyramid as a coordinate. This number sequence of this coordinate matches exactly the speed of light traveling through space, measured in meters per second. This is amazing stuff.
How did humans with no cranes, no modern machinery, move such colossal stones with such precision? Experiments and studies suggest sleds, ramps, and ingenious labor coordination, yet the project remains almost inconceivable in its scale. Every year, researchers revisit the pyramid to understand its construction methods. Despite this, no one disputes its size and the precision of its alignment, aligned almost perfectly to true north. A structure of such magnitude, built with tools of its time, defies ordinary expectations of human capability. Thousands of kilometers east, the Great Wall of China stretches across deserts, mountains, and plateaus. Built over centuries, with the earliest walls dating to the 7th century BC and major construction during the Ming Dynasty, 1368 to 1644 AD, it spans an estimated 21,196 kilometers today, including natural barriers and trenches. Its sheer length is staggering. Towers, battlements, and fortresses along the wall required coordinated logistics, vast amounts of stone and earth, and generations of labor. When viewed from above, the wall seems to snake endlessly across the landscape, a human imprint impossible to ignore. Even modern satellite imagery struggles to capture its full extent in a single frame. It exists as a testament to organization, endurance, and ambition, yet its scale continually invites disbelief. Humanity has not stopped there. The Three Gorges Dam in China, completed in 2012, is the world's largest hydroelectric power station in both installed capacity and sheer size. The dam stretches 2,335 meters across the Yangtze River, stands 185 meters tall, and contains over 27 million cubic meters of concrete. It required the relocation of over 1.2 million people. The structure produces nearly 22,500 megawatts of electricity, enough to power millions of homes. Its scale is monumental, and yet, even with modern engineering, building something of this size involves risks of unprecedented proportions, structural integrity, water pressure, and seismic stability. That it exists today, functioning safely, is remarkable. Nature, however, produces structures that rival humanity in size, but with forces that are incomprehensible in their own way. The Mauna Loa volcano in Hawaii is the largest volcano on Earth. Measuring over 33,500 feet from its base on the ocean floor to its peak, it contains an estimated 18,000 cubic miles of rock. Its eruptions have reshaped islands, buried forests, and redirected rivers. No human could replicate such volume of material, nor could we manage its internal heat, pressure, or eruption patterns. The scale of this natural structure is staggering, and its longevity, spanning hundreds of thousands of years, seems almost impossible when compared to human lifespans and civilizations. Another natural formation of extraordinary scale is the Great Barrier Reef. Stretching over 2,300 kilometers along the coast of Queensland, Australia, it is the largest living structure on the planet, visible from space. The reef is home to thousands of questions about the limits of natural architecture. Space itself offers examples of structures that dwarf even our largest constructions. The Valles Marineris Canyon system on Mars stretches over 4,000 kilometers and reaches depths of up to 7 kilometers. By comparison, Earth's Grand Canyon is 446 kilometers long and just over 1.8 kilometers deep. Valle Marineris is not only enormous but geologically complex, carved over millions of years by tectonic forces, crustal stretching, and possibly water or lava flows. Its size, combined with the precision of its cliffs and valleys, makes it a structure that appears almost deliberate, yet it is entirely natural. Back on Earth, modern engineering continues to challenge human perception of scale. The Burj Khalifa in Dubai, currently the tallest building in the world at 828 meters, required over 330,000 cubic meters of concrete and 103,000 square meters of glass. Engineers faced unprecedented challenges: wind load, temperature fluctuations, vertical transportation of materials, and structural integrity at heights never attempted before. To date, the Burj Khalifa stands as proof that humans can overcome seemingly impossible limits. Yet when first proposed, its height and construction methods were widely considered unrealistic. Today, its existence validates human ingenuity, but continues to push the boundaries of what we assume is possible. The Panama Canal, though smaller in vertical scale, presents another example of human structures that challenge expectations. Completed in 1914, it connects the Atlantic and Pacific Oceans, spanning 82 kilometers. Construction required cutting through mountains, controlling water flow with locks, and managing disease among tens of thousands of laborers. Its completion revolutionized global trade, yet the technical difficulties and human cost made its success almost inconceivable at the time. Among natural structures, Mount Everest itself represents a scale humanity can only observe, not replicate. Standing at 8,848 meters above sea level, it formed over tens of millions of years from the collision of tectonic plates. Its jagged ridges, sheer cliffs, and unpredictable avalanches create an environment so hostile that even modern equipment struggles. It dominates the landscape with a scale and endurance that outpaces anything human can create. Even when human-made structures are not as monumental as the Great Wall or Burj Khalifa, some remain puzzling due to engineering precision. Consider the Panama Pacific Exposition Tower, built in San Francisco in 1915. Though smaller than modern skyscrapers, it required precise construction techniques to withstand earthquakes, something only realized in the 20th century. The expertise applied decades before modern structural modeling shows how ambitious construction sometimes outpaces contemporary understanding. Modern observation technology also uncovers structures in nature that defy expectations. The Mariana Trench, the deepest part of the world's oceans, plunges nearly 11 kilometers below sea level. Its walls, trenches, and underwater ridges represent enormous structural forces at work. The pressures at these depths, over 1,000 times atmospheric pressure, make the trench a landscape entirely beyond human creation, yet completely real. Organisms survive here, and even submarine technology must adapt to these conditions. Its existence reminds us that natural scale can exceed human engineering by orders of magnitude. Large artificial structures also create unforeseen consequences. The Three Gorges Dam caused seismic shifts and water displacement across an area of 1,084 square kilometers. The human impact, environmental changes, and maintenance of the largest hydroelectric structure in history highlight how scale introduces unpredictable complexity. Even when fully planned, structures of enormous size interact with natural forces in ways that seem almost beyond control. The International Space Station, ISS, represents another kind of scale. Measuring 109 meters across, with modules launched over decades, it required international coordination, precise orbital insertion, and engineering in zero gravity. Its longevity, continuously inhabited for over 20 years, proves human capacity to sustain enormous systems in harsh conditions. Yet even here, every module and system must be carefully maintained. Mistakes can be catastrophic. The scale is technological, logistical, and human, combined into a single living structure orbiting the planet. Natural megastructures also exist in the sky. Jupiter, for example, is a gas giant with a diameter of 139,820 kilometers, containing 318 times the mass of Earth. Its Great Red Spot, a storm larger than Earth itself, has persisted for at least 400 years. When measured in scale and persistence, Jupiter and its storms create structures that no human technology can approach. We can observe them, map them, simulate them, but to replicate them would be impossible. Even the largest known stars challenge our conceptions of size. Scuti, a red supergiant over 1,700 times the radius of the Sun, could engulf Jupiter if placed in the center of our solar system. Structures on such scales are so far beyond human experience that our minds struggle to comprehend them, yet they exist, entirely factual, measurable, and undeniable. History, technology, and nature repeatedly show us that scale is not merely about size. It is about endurance, precision, and coordination. Whether it is the Great Pyramid, Mauna Loa, or Valles Marineris, the largest structures reveal a combination of forces, effort, and physics that seem almost impossible. They force us to confront limits: the limit of human coordination, the limits of material strength, the limits of time, and the limits of imagination. Some structures are both natural and human-made. The Hoover Dam, completed in 1936, is 221 meters tall and 379 meters long. It required 3.25 million cubic meters of concrete and remains an iconic symbol of 20th century engineering. Its scale, construction timeline, and ongoing maintenance make it a modern marvel. Engineers at the time were constantly solving problems that would now be considered basic, yet the dam continues to function nearly a century later. In space, asteroid impact craters illustrate how natural forces can build and destroy on massive scales. The Chicxulub crater in Mexico measures over 180 kilometers in diameter, created by an impact 66 million years ago. Its formation released energy billions of times more than modern nuclear arsenals. A structure of that scale reshaped the planet, ending an era and paving the way for another. No human creation can approach this energy, yet the crater remains, preserved beneath layers of sediment, a lasting reminder of forces beyond our control. The Panama Canal, the ISS, Burj Khalifa, and the Great Pyramid, all human-made, share a common theme. The larger the structure, the more improbable its existence seems. And nature is no different. Volcanoes, canyons, reefs, and stars remind us that scale is as much about endurance as size. The largest structures, whether forged by humans or formed by nature, challenge our understanding of possibility. They should not exist, yet they do. They endure. They persist across centuries, across millennia, across time and space, as monuments to forces both known and unknown. Their scale forces us to confront our assumptions. They force us to measure, to calculate, to question, and to marvel. And as we continue to build, explore, and observe, the largest structures on Earth and in the universe will remind us that ambition, scale, and endurance are not limited to human imagination. They are fundamental laws of reality itself. If you want to explore more incredible structures, both human-made and natural, and understand the scale, engineering, and science behind them, subscribe to our channel and turn on notifications. The story of the largest structures is far from over, and each discovery brings us closer to understanding how and why they exist.